You guys are looking at me like I need to do something.
It starts with you.
I'm Martin Wallace.
I'm Darren McCarthy.
And I am Dan Fury.
And this is The Fundamentals. So, what are we talking about, Kaz?
Gravity.
Talking about gravity today.
Mm-hmm.
We're talking about gravity.
You know, it's on everybody's minds.
It's on everyone's bodies, I think.
It's the real deal.
I'm sick of sounding like a broken record on this podcast.
This is just too big of a topic.
It's not unbelievable.
I feel so dumb so quickly in some of these topics we picked.
Derp.
Some of the equations.
Because we're talking about...
I don't even know how to say the equation.
We are talking
alone.
about extremely scientific stuff here. Like stuff that no one fully comprehends.
Martin, how do you feel about this?
I had a blast with it.
I had a blast with it.
Yeah,
It's fascinating. But I really feel like I need to go back to school. Like
true comprehension of that.
That's why we do this.
Yeah.
Mm-hmm.
I think fundamentally a couple of things that stuck out to me is we think about gravity as being this force that is exerted on us at all times, in all objects. This force is pulling us
we are
to the Earth.
With gravity.
Yeah, so gravity's pushing us down here to the Earth.
Or pulling
us down to the Earth.
Now, this is a Newtonian outlook at gravity.
And I think
Newton.
If you said, okay, so objects attract each other, and then, you know, the bigger the object, the greater the force of attraction is going to be. It follows. Like you can kind of wrap your mind around that. So you just say, okay, so things are like magnets. Like if you were explaining this to a kid, it's like, things are like magnets. The bigger the magnet, the greater the pull it has.
Not scientific whatsoever.
Not scientific whatsoever.
But it makes sense.
It makes sense. And you can but if you really get into it and try to dissect it mathematically, things fall apart.
Mm-hmm. This was the biggest shock to me. I suppose it wasn't that shocking, but it was just nice to hear this from the scientific community as far as we've gotten in science. Mm-hmm. What we know about gravity is that we don't have a clue what it is.
We can describe its effects,
we know what it does,
but we can't describe what it is.
No idea.
Did anyone really know what it was until people tried to go to the moon and then they were floating all over the place?
No.
How did you really... I mean, yeah.
So Newton discovered...
Galileo, even before Newton.
But wasn't that the first time that it was experienced, that you were relieved of gravity?
No. Free falling. Anytime you free fall. Skydivers, parachuters. It's the same effect. 0 Gs.
But did they really understand that?
But if you're free falling, you are... Everything is free falling all the time.
Yeah.
You're still at the mercy of gravity. The idea of free falling, as we would experience, like on a roller coaster going down an incline, you know, the sharp incline, you're accelerating at a greater rate.
Yeah.
But the reach of gravity is infinite because it's essentially massless. It's not like sending out particles that are like then grabbing something and then pulling it back. One of my favorite kind of quotes, I guess, I came across was Neil deGrasse Tyson. I think he was quoting Einstein. He referenced Einstein when he said this. I'm not sure if it's a direct quote. So this is kind of like a third party quote.
Space and mass and...
Yes. Mm-hmm. So
quoting Einstein.
Yeah. So matter shapes space and space moves matter. So matter tells space what shape to take, and then space tells matter how to move.
Okay.
Pretty easy way to picture it. How Einstein described gravity is mass curves space-time, but that matter is moving in a localized linear line. So we're moving in a straight line on the local scale. So like the idea of like picture like a funnel, a giant funnel, and if you just walked in a straight line, you'd be actually going around in a circle, like on this curvature, but you would be walking in a straight line. That's kind of like the visual that I got, and I really like that. The idea of like there's these things that are just they're changing the shape of the straight line that you're walking on.
Depending on its mass.
So
easy way to visualize it's like a sheet of rubber or a trampoline. Mm-hmm. And then think about putting a bowling ball in the middle of a trampoline. It's going to sink down. Now, all those lines are still straight. but they're bending to the weight of the mass in the middle. And so when you have something in orbit, like a ball rolling around the bigger ball, you have essentially the effect of gravity on space-time creating this orbit, right? Mm-hmm. But that is looking at space in a section of 2 dimensions. So it's almost impossible to do, but imagine that in 3D and the effect that it's having. So we can do that mathematically, but trying to imagine it's much more difficult.
Yeah.
So that's Einstein's take, and it took 300 years between Newton and Einstein to change that. So Newton's whole thing was it's a force. We have no idea what it is, but it's a force. But it's not.
It's not a force.
It's not a force at all. It's a bend in the fabric of space-time, which is Einstein's whole theory of relativity.
So what Newton was describing, the apple falling on the head, that whole thing, it's essentially it's saying that mathematically there must be something doing this. So his equations were used, a couple hundred years after his death, but they were the groundwork for predicting that Neptune existed. So no one had seen Neptune.
Amazing. Yeah.
No one has seen Neptune. People had seen, cheap laugh, Uranus. People had seen Uranus, and because
Uranus. It's Uranus.
Is it Uranus?
I think they changed it just to stop all the elementary jokes.
All right, let's go back. Uranus. People had seen Uranus. Am I saying? I'm saying right.
Yeah.
In charting its path through the solar system in relation to the other planets and just astral bodies in our solar system, they said, well, there must be something else out there to square up Newton's equation. And so then there was a German scientist, Gala, I think was his last name. He's an astronomer. Someone else had done the equation and saying, okay, well, look at this spot in the night sky with a telescope. You should see something. And this guy looks, and it was within 1 degree, which if an astronomer said well, that's actually a big difference, I would believe them, but I still think it's pretty crazy that
the fact that they could even predict that it was there without seeing it. It was all
conjecture.
They could see that something should be pulling on it.
Yeah,
it's there, and they were right.
Right. Which, talk about that. What a good moment that would have been.
Speaking of planets' orbits, something I learned I thought was pretty fun was there's the idea that the planets orbit in ellipses.
Mm-hmm.
False.
Mm-hmm.
False. It's false. Yeah, that's a overgeneralized way of thinking about it. They orbit in conic sections. So if you were to take something like, an easy visual for this is like those little paper cups that you get at little water fountains.
Yeah.
Those little cones.
Mm-hmm.
So if you were to take one of those and cut it across, you have a circle. If you were to cut it at a slight angle, you would then have an ellipse. And then you can keep cutting it, and that's how the orbits work. See how far across it is on a cone, which is why if you cut it too extreme and have ends, that's how you get something like a comet. It's still on an orbit,
but it's just
but it's not on an
crazy direct path.
Mm-hmm.
Yeah,
man,
and that's how they can determine real proper orbits. So much so that we can fly a spacecraft at Pluto and hit it 9 years after we shot it out and know exactly where it's going to be. It's crazy. And so gravity, even though we don't know what it is, even theoretically, we know how it works to such a degree. It's bizarre. So it's one of 4 major forces. These forces that exert with no connection between objects.
Mm-hmm.
There's gravity, we're all familiar with. Electromagnetism, which we're all fairly familiar with.
Mm-hmm.
And then the nuclear forces, called the strong and the weak force. So that will all need separate podcasts. But essentially the idea here is gravity is without a doubt the weakest of the 4 forces.
By an order of
an unbelievable
10 to the
magnitude.
38.
Whoa.
Put it this way, electromagnetism, the next force, is so much stronger than gravity that cheap whatever magnets that you buy at whatever stores, refrigerator magnets, easily defeat Earth's gravity.
Whoa.
When you put them on a refrigerator. takes no effort at all for electromagnetism to just totally overcome. Now, the weak and the strong force, unbelievably strong. But the thing is, they only work in a tiny, tiny area.
That's where quantum mechanics comes in. So
they're affecting the nucleus of atoms.
So the strong force was binding a proton and neutron together in an atom. And at that scale, gravity, this is another awesome, I watched a bunch of videos of Neil deGrasse Tyson. I think he's really funny. And
he's great. He's
awesome.
Definitely Carl Sagan of our time.
Yeah, and
he makes it approachable.
He makes it fun. Yeah.
It's incredibly smart, but it's not just reading a paper.
Yeah, I think he was a good fun kind of resource for this podcast, especially. Yeah. So all kudos and shout outs to him. And he was talking about if we were like insects, like crawling on the ceiling and just seemingly like just able to stay there, like the insect scientist would not have discovered gravity at this point because it does not affect them.
That's so weird.
And then he was talking about it, the scalability. So there are these the Jesus spider that it can like essentially walk on water.
Yeah.
Because it doesn't break the surface tension,
it's
right?
far more concerned with the surface tension of water than it is with gravity. So it wouldn't even think about gravity because at its level, the surface tension of the water is far more important.
Paramount.
Now, instantly, I don't know if it made me think, what are we missing at our scale
What's
of
the next
existence?
Force that we have?
What's the force that's acting on, like, I don't know, like the moon that because we aren't that big, we
don't even have an antenna to pick up the signal.
Yeah, whatever.
There's nothing.
So we can see, we can observe the effects of gravity. We can
That's
measure
a fun thought experiment.
Measure the effects of electromagnetism, the strong force, the weak force. There could be 50 other forces.
That's just our range.
That's the range that we can observe and pick up.
It's like another way of thinking about that is a fun thought experiment. When you like light, we have these organs that are highly tuned to a very, very small specific
bandwidth,
breadth of
or
the wavelength of light. Then you have X-rays, microwaves, UV light, this incredible spectrum of light that's out there we have nothing to do with. We have instruments that can pick it up, but we can't see it. Now, can you imagine what we're missing just because we don't have the organs to even know that it's there, let alone to be able to get the technology to look at it closer? Things out there that were just all super theoretical, of course, but it's a fun thought experiment. We're only observing
the way we are observing,
the way we were built to observe.
Yeah.
We're
doing it because that's the way we're doing it.
Just like a Jesus spider.
Mm-hmm.
Yeah.
Whoa.
Another thing I really liked was, and maybe you came across this too, was the idea that the effects of gravity are acting the same rate as the speed of light. So if the sun like burnt out, it would be 8 minutes before we would stop seeing the light, but it would also be 8 minutes until we stopped feeling the effects of its gravity.
A good way to visualize this is ripples in a pond.
Mm-hmm.
Okay. So if you were to throw a rock into a pond, right? Or a trampoline's even better. Let's think about it like that.
Yeah.
But that's the gravitational waves, which are only theorized. And we have like this really amazing stuff set up to detect them if they ever come. It's again like trying to find the planet based on the math. We know something's occurring, so we're looking in specific ways to try and detect it. So if you had this bowling ball on the trampoline again, and we had a rock or a marble rolling around it, if you were to slow that down and watch it orbit, roll around, that would start to make a little bit more sense as the Earth around the sun. And then if you were to take the bowling ball off, the marble wouldn't instantaneously shoot out.
Right.
What would happen is there would be a wave starting at the center of the mass of the bowling ball that would go up and create a ripple in the trampoline that would take a certain amount of time to hit the marble. So for a period of time, the marble would have no idea that anything had even happened, just like we would have no idea that the sun disappeared. And again, this is a 2D example of a 4D plane, but that's the idea. It can only travel so fast. It doesn't happen instantaneously.
I think that ties into just the way that we observe. We, far and away, as humans, experience the world visually, or we rely on our visual senses so much more than most species of everything else on planet Earth. And I feel like I've heard that, oh yeah, it takes light 8 minutes to go from the sun.
Yeah.
Travel 93 million miles, hit the Earth. And then it's like, well, yeah, so if the sun burnt out, we wouldn't know for 8 minutes. But never is it really discussed that, like, what would actually, it's not just like the lights would go out. It's like we would be thrown, like the Earth would be
shattered. We would be thrown, yeah. The tides would go crazy. We'll talk about tidal forces in a minute. Not only would it be dark, but it'd be incredibly cold.
Oh, it'd be so fucked
instantaneously,
up.
though.
So
like,
there would be no source of heat.
Yeah.
At all.
I mean, how soon would humanity die off?
Instantly.
Yeah, absolutely.
I mean,
within 8 minutes.
Well, think about like what. There's no more energy coming to the Earth.
Yeah, energy's done.
And the gravitational force, it's like a shock wave on
the atmosphere would totally crumble, would just decompress. There's nothing holding.
An order of magnitude that's like, think about like, so the sun is so massive, it's able to hold the Earth in orbit.
This whole solar system.
If it blew up, it's like, it's not just like the house would fall over, like the Earth would like fall apart.
This is
you
too
got to
scary.
think. So, like Jupiter, a fun fact: Jupiter has like 243% the gravitational pull of Earth. It has its own body. So if you were standing on Jupiter's theoretical land, which it doesn't have, but if there was a place on Jupiter that you could stand, you would weigh 2.5 times as much as you do. It would cost that much more effort for you to move your body.
It'd be 110
slow motion.
pounds.
What are you 25 pounds right now? Soaking wet?
Soaking wet.
But it's way, way farther out than Earth. And it's still caught in the sun's pull effortlessly. It's so much bigger, so much denser. I don't think denser is the word. It's so much more mass because it's actually less dense, I think.
Yeah, I think it's less dense, but it's more massive.
I don't know. This isn't about Jupiter.
What about Pluto?
Pluto is...
Is it still a planet?
It's a planet. It's cruising. It's fine.
I want Pluto to be a planet.
Jupiter like is a really fun... Because it's gas, right?
Mm-hmm.
There's no...
Huge ball of gas.
When the sun was forming, it was a giant cloud of gas. Basically, starting with... It's just like... making like a ball of clay, and you were just constantly adding more and more clay. So you could start off with like, just kind of rubbing just between your fingertips, like a piece of clay making a ball. It's like, it's nothing. But then you talk about like scaling that up into something that's actually going to hold itself together and be like,
by its own mass.
By its own mass. It's like, it's separate. It's its own object.
Mm-hmm.
Jupiter existed a little bit the gas that made up Jupiter existed a little bit too far out of that zone where it would have formed with the sun or would have dissipated. But it was like a ring of gas around this central ball of gas that ended up forming the sun because the gravity pulled the molecules and atoms that ended up making up the sun together. And then because they were so concentrated, the density became so great, essentially it just started like a nuclear fusion reaction.
Friction heat, right?
Yeah. So there's so much like gravitational force acting between the atoms, it started a nuclear reaction.
Holy shit.
Jupiter was outside of that. There wasn't enough gas for Jupiter to become a sun or star.
What the fuck?
But that gas couldn't escape.
Big enough to hold itself together.
To form, yeah.
You guys are doing really great tonight, I gotta tell you.
This is like the most fun stuff. I just want to do astronomy from here on out.
I want to do astronomy all the time.
So gravity, real fun fact here. It's based on a thing called an inverse square law.
Yeah.
So Newton invented calculus.
Is that math?
Yeah. Newton invented calculus.
Think about that.
Mostly to deal with...
That guy's a jerk.
Let's just take 10 seconds to think about this. Newton invented calculus.
No, it's hotly debated.
He is to blame.
There was another guy who said that he did it was like roughly in the same set of years. They both discovered it sort of independently, but Newton's way more of a badass.
Yeah.
And we should definitely do a podcast on Newton.
Yeah.
There's like a lot of great.
Principia.
Mm-hmm. He was a just total badass.
Save it.
Okay, sorry.
And so he invented calculus. The thing with gravity is the inverse square law. So if you get double the distance between two objects, gravity is pretty much based entirely around mass and distance. If you double the distance, you lose 4 times the amount of gravitational pull influence. But the beautiful thing about it is that it can never be zero. It can only get smaller and smaller, which means that not only is the sun having a gravitational impact on a star in a solar system on the other side of the galaxy, but it's also having an effect on every galaxy in the universe, every star in the universe. And the thing that really blew my mind was that so do I.
Yeah.
It's incredibly small, so much so that it would never really affect anything. But I have a force connected between me and every single thing in the universe. It's crazy.
Whoa.
So Newton's, his equation is F equals G times M1, M2 divided by R squared. F stands for force, G, gravitational constant, M1 and M2 is the mass of each individual object, and those two they're multiplied by each other, then divided by the distance between the center of each object. So gravity there's no limit to its reach. So what Corey is saying is that we could find out the gravitational, using Newton's equation, the gravitational pull between you and Martin Wallace.
Whoa.
This is a fun thought experiment for me, too, about gravity and how weak it really is. You don't feel the difference between being out in the middle of the woods, gravitationally, and being in the middle of LA, surrounded by 13 million more people and the weight of all the stuff that was brought to that area. You don't feel that difference whatsoever. Nor do you hardly feel the difference between being at sea level or being high up. You feel air pressure differences.
Yeah.
And there is a difference too, gravitationally, between depending on where you are on Earth, even localized is different.
There are places in Canada that have way, way less gravity.
Way less. And it's like, talking about like the density of the Earth that you're standing on will affect the effect of gravity on you.
But you never notice it. It's way too
I
light.
love that you just differentiated between effect and effect.
I think I've already said the same word twice, but I gave more. Yeah, but thank you.
Oh, you were talking about the centers of objects.
Yes.
That's another funny thing about gravity. It doesn't matter if you were to stand on the Earth as we are, big spherical object, or an object with the same mass localized into a tiny, tiny ball that had a platform that was 4,000 miles out, and you were standing on that because it's only about the center.
So the center is, the centralized point of all the density of that object. This is where like a black hole is different from.
It's only a matter of time.
Well, I think it's the most interesting.
There's no doubt. Yeah,
it's the most interesting thing.
The craziest.
It's the craziest thing of all time.
Mm-hmm.
So our sun is going to die in 4 or 5.
No, it's not.
It's going to make
It's
it, man.
never going to die.
It's literally going to eat itself to death.
It's literally going to eat itself to death.
It's going to run out of energy.
When the universe was formed, it was hydrogen atoms just spread everywhere.
Little baby hydrogen.
Little teeny tiny baby hydrogen atoms swimming along. And so, brief explanation of what a black hole is and how it relates to gravity. As a star dies, what's actually happening is the hydrogen atoms that make up the star have been fusing together through nuclear fusion. That reaction is kicking off photons of energy, which we experience as light and heat. When those two hydrogen atoms fuse together, they become helium, I think, is like they just move up the periodic table of elements. So like the
heavier and heavier elements.
So the atomic weight of a hydrogen atom is a 1, helium's a 2. When you get up to the point of iron will no longer continue that chain reaction. So as the star is fusing, and this is something to keep in mind, that this is happening billions of times every second, maybe even trillions of times every second of every day.
I have no actual reference point to imagine the sun.
It's insane.
It's so big.
So
no way to even consider it.
It's not real.
Cannot
shoots
consider
of gas that would just swallow 30 Earths.
Yeah, for no reason.
And that's just
oh yeah, I burped.
You have no real frame of reference for the size of the sun.
So these reactions, as the elements get heavier and heavier and heavier, the center of the sun is becoming, essentially, it's more dense. So more material, the heavier elements are gravitating towards the center of the sun. The reactions of the heavier elements become more and more robust. The sun begins to expand. I'm talking about over like millions and billions of years. So the sun is going to gradually get bigger in size. The density won't change, but it's going to expand. And it will eventually be so large it swallows the Earth. And I think it goes even further into it hits Mars, I think.
Now, different types of stars do this whole process in different ways,
and
depending
it all
on the
depends
size of them.
on the size, the density, the amount of material that makes up the star.
Density is the biggest point here. Mass, how much something weighs, density, how tightly compacted it is together. And that's very important when it comes to black holes. It's about how dense it is, not how much it weighs, but the density of the object.
Our sun will eventually become like what's called a white dwarf. If it were 3 or 4 times larger, it would become a neutrino star. If it were, I think, like 5, I'm not sure exactly like what the cutoff point is, but I think if it was like 5 to 7 times larger, and then there's some that are even larger than that, 7 times larger, the density of it. So essentially what happens is the gravity always wins. So these reactions, the nuclear fusion reactions between heavier and then subsequently heavier elements, as it burns up the easiest fuel possible at all times.
Remember, like fire does. It always finds the easiest route.
The easiest route. So hydrogen's the easiest.
It's so simple.
Once all the hydrogen's gone, the helium's the easiest. By the time you get to iron, though, the reactions they're more and more force is exerted to fuse these elements together. And so it's creating bigger and bigger explosions. The star is expanding and expanding. Eventually, it runs out of fuel and gravity wins. So the center of gravity of that body is going to eventually pull all of its matter and mass back to the center. If it's dense enough, it will then become a black hole. Our sun is not dense enough. There's not enough matter. So it would become like a white dwarf, which is like this super burnt up white hot ember, essentially. Even like in the dead of space, it's going to be super hot. And it's this white ash, essentially, that's like super fused together. That's going to be the center of what is left over of our sun. Stars that are large enough, the gravity is so strong, it bends light into itself to a point where the gravity, the density of the object is affecting the curvature of space-time in such a degree that even light can't escape on those. The straight lines that we talked about don't exist. Like they're not. They don't matter anymore.
And that's what you're talking about when you talk about a black hole. It's black not because there's nothing in it or nothing to see, but because light cannot escape for you to see anything. Yeah. And that's a fun idea is inside a black hole, it's not dark at all. It's full of
all
it's the most beautiful thing ever.
It's full of everything. Everything around it is like it's eating. So what the stars will do is when the density becomes so much that they'll compress atom to atom unbelievably tight. And then it'll compress nucleus to nucleus. There's literally no room for anything to move around. And then it'll compress in on itself and become so dense that light can't even escape it. There's no room in it to do anything. And it eats everything around it and holds onto it. And so the mass of these black holes is directly proportional to the mass of what it eats. It's just denser.
It's getting bigger.
It only gets bigger. And for a long time, we discovered these things and how you see them in space is light does a really weird thing where it reflects
Refracts.
Yeah, refracts around it so that things
I love
behind it
that word.
actually become bigger. So there's a lot of odd light formations happening. We had no idea what was going on. And, out in space, it's just everything's dark anyway. But then you also see that there's all kinds of movement around them. Stars are moving way too fast because they're so close to the event horizon. They're being pulled, the same way the Earth moves faster at certain points of the foci around the ellipse or the conic section as it moves around the sun.
We should talk about dark matter a little bit.
Should we?
Please.
The overall structure of the universe as we observe it accounts for something like 4% of the observable matter, which is hard to think about. All right, so the total mass energy of the known universe contains 4.9% of ordinary matter, you and I in the stable. 26.8% is dark matter. 68.3% is dark energy. That doesn't make any sense.
I don't know what any of that is.
Dark energy.
So basically, what we're looking at is the laws of nature, the laws of physics that we have right now. All we really know is we don't have all of them.
Not even close. It probably goes back to our perspective.
Yes.
What can we observe?
I think so too.
Can we ever?
Yeah,
I like to think
probably not us. But I think
someday.
I think our technology will.
Mm-hmm.
I don't think that human beings will. This is again a much
Our technology will.
yeah.
No, if we create AI,
I think
absolutely.
If we create a system of artificial intelligence that
An
in
immortal
a week,
being
that in a week is running 20,000 more computations per second than any human being ever could. So in a week, it's doing 10,000 years of human development.
And put 7 billion of those together. And it doesn't have the limit of having to run off the same types of energy that we do, organic matter. And it doesn't have to worry about morality issues. It doesn't have to worry about pain or sleeping or anything even like that.
Whoa.
Yeah. But you and I...
This is science fiction, though, but I don't think it's that far away.
I don't think so either.
We have no idea.
I think, they say, like, so if things are doubling every minute, like 11 and 12 o'clock, if things are doubling every minute, it's like, at what minute are we halfway there?
Oh, yeah, you're the 30 seconds to midnight or whatever.
Exactly. The point being, it's going to be we're so close to it that we won't even know how close we are to it.
The way that I had heard that is if bacteria in a cup was doubling every minute, right, for an hour, and in that hour, I suppose, at what point was the cup half full? It's a minute. It's at 59 minutes.
Yeah, 11:59.
It takes so long for it to get there, but once it's halfway, when it doubles, it's more than it's been the entire time. And so technology compounding is that same way.
Another Einstein quote, the greatest force in the universe is compound interest. I think that's something that like that does really tie in with gravity too. It's like with a black hole, especially, it's adding more of what's fueling it at all time, which is matter, which is it's not a force. It's not like forcing the same way like the strong nuclear force and the weak nuclear force are forcing things, but it's shaping the universe.
When we initially discovered them, we thought they were a rarity, some sort of terrible, hellacious storm of a force. It's like it's the most destructive thing you can imagine. But now they're pretty confident they're what is the center of galaxies.
Yeah.
We have a supermassive black hole, a black hole so big that it gives our galaxy its shape. Our galaxy rotates around the thing the same way we rotate around the sun, right? And we're 20,000 light years away from it.
No.
Yeah.
That can't be a thing.
Absolutely. Every galaxy.
Hundreds of billions of galaxies.
And it's just eating the stars. It's slowly getting them, and it's just growing bigger and bigger. That's what we're rotating around. And I just went to the planetarium this last week. It's amazing. Watched a video on black holes that was narrated by Liam Neeson.
Oh my God. Shit.
It was so fun. So there's an astronomer who's been watching the speed of stars at the center of our galaxy. and they are moving around this thing at an unbelievable pace. And I watched their trajectory, like going around in the star map.
Unbelievable.
It's crazy. And
How
they're
fast?
it's not even worth mentioning. it's there's like no speed to compare it to. It's just being pulled around a black hole that's so big that it's holding our galaxy
Like
together.
me on a skateboard,
Yeah, but like
me in a bike, me in a car,
Me
Yeah.
on anything that would move
a
faster than I
Lamborghini
can.
Countach.
jetpack,
Yeah. It's just
ice luge.
bizarre.
So our sun is going to burn out
It's got several
No, it's
billion
not.
years, right?
several billion years.
Mhm.
Are we going to get sucked into that giant black hole at the center of our galaxy before that or after that?
Oh, it'll take us so long. It takes 20,000 years for light to reach us from there.
Yeah.
That might be the whole span of the galaxy, the Milky Way, but either way, it's an enormous distance. We'll never get there.
Okay.
Like,
Ever?
it's taken us so long just to get outside the solar system. If we were to travel the speed of light,
20,000 years.
it would take us 20,000 years. You could wormhole it,
Put a
but nobody really knows what that is. Yeah. So, and that you're talking just our galaxy, you know. The next closest galaxy is astronomically farther than that. The sun will die out long before, because we're on the edge too. It's an interesting thing to think about. We could be in the middle of the galaxy instead. When you look out, it's more dense with stars. We're actually on the lighter side. When we look up at the night sky,
I think in the darker places on Earth, like with less light pollution, you can see 3,000 stars with the naked eye. I
Mhm.
think in most places on Earth, you can see
15.
15, 3,
like a dozen
Yeah.
stars.
like
Mhm.
not
More or
enough.
less.
You still get Orion's belt and a little bit of the Big Dipster.
You know, Orion was my first dog's name.
Oh, that's cute.
And there is no chance I can look at Orion's belt and not feel strong feelings.
That's so much better than my connection with it.
What is it?
Men in Black. The galaxy is in Orion's belt.
That's why I cried during Men in Black. That's why I'm gonna.
Has there been any first-hand accounts of astronauts who have experienced the relief of gravity? What it feels like?
They're actually moving a lot faster.
When they're in space,
Depending
they're
on- yeah.
floating around.
Sure.
Gravity.
That's what we call it.
Gravity is affecting them. They're further away from the center of the Earth. They're moving way faster than we are on the surface of the Earth. But if you just let the International Space Station sit in orbit, they're falling.
Has anyone described what it feels like to be in space?
It feels the same way as when a plane is crashing.
How about that?
Well, how do we?
You fall. You're constantly falling.
How do you describe that?
There's no difference. This was one of Einstein's theories. This is what led him to come up with so many things. Was he realized that free falling and what was it? This is the elevator experiment.
Yeah.
When you're free falling in an elevator, that's no different than just being out in space.
What about when you go over a really exaggerated hill in a car, and
that you kind of lose that feeling in your gut?
You boys know what it feels like in your balls.
I don't think that's what astronauts feel, but maybe
It's got to be similar.
I bet it's like
gotta be related.
way more intense. Once you're out there, you don't feel. I mean, I don't know, so
Yeah.
I haven't done it, but it
Yeah, exactly.
The first hand accounts I've heard about being in space, like for a spacewalk.
Yeah.
I forget what astronaut this was, but they were asking like, so when you're moving out in space, like, what's it like? You're moving in slow motion. It seems like you see the astronauts they're out like moving these solar panels around. They're trained to slow down so they don't make a mistake. So when you see an astronaut and it looks like he's or she is moving in slow motion, they're actually following their training protocol and slowing down and doing things correctly. If they wanted to wave and do them like, I guess the moonwalk out in space or something, they could do it. Because you're talking about just their muscular reflexes. If they had something rigid to hold on to that they could then exert force on, they could do it.
They propel themselves faster than you could on Earth if you jumped.
Way faster.
Yeah. I have an excellent quote here from astronaut Barry Wilmore, one of the true gems of the internet.
Oh, look him up.
Barry Wilmore.
Hey.
To answer your question.
Yes, please.
First-hand astronaut experience. Barry Wilmore says, "You never know true beauty until you see Earth from space, or true terror until you hear someone knocking on the space station door from outside. You look through the porthole and see an astronaut, but all your crew is inside and accounted for." He used the comm to ask who it is, and he says, "He's Ramirez, returning from a repair mission. But Ramirez is sitting right next to you in the command module, and he's just as confused as you are. When you tell the guy this over the radio, he starts banging on the door louder and harder, begging you to let him in, saying he's the real Ramirez. Meanwhile, the Ramirez inside with you is pleading to keep the airlock shut. It really puts life on Earth into perspective."
What the fuck?
Okay.
Isn't that great?
What?
All right.
Fuck.
Can I ask the listener here? That's Barry Wilmore.
Barry Wilmore.
Who the
yeah.
fuck is Ramirez?
Can I ask the listener to look up an image search of Barry Wilmore?
Mhm.
Once you have a good image, hit pause, look at that, and then hit play again and listen to the description of what Barry fucking Wilmore said.
Ramirez.
What the hell?
The internet's great. Hopefully you paused and went back and, didn't have the story spoiled for you, but fake.
Whoa.
You guys learn about tidal forces? You know how tides work?
Yep.
Tides are great.
Well, it definitely has something to do with gravity.
It does.
It
It
does.
has a lot to do with that.
So how tides work is lunar gravity, actually.
Sure,
the sun
the
has
moon.
something to do with it, but not quite as much. So when the moon sits, just to make it easier for the listener to imagine, the Earth and the moon sitting directly above it. The moon is pulling the oceans up towards it, everything on the northern hemisphere, but it's also pulling the Earth. So what you have is the oceans are pulled up towards it the most, then the Earth is pulled up a little bit, and so it causes a high tide on both the top and the bottom of the Earth because it's pulling the whole thing up, but in its own little sections. So the bottom of the Earth is experiencing a high tide because the ocean isn't pulled that much, but the Earth is pulled more, so it separates. But the exact opposite is happening on the top because the moon is pulling the ocean more than it's pulling the Earth. So it goes up. But then from the sides, it's being pulled in, up towards. So when the moon comes down a little bit is on the side, you get low tides on the top and bottom because the Earth is being stretched towards it, and so are the oceans this way.
The theory is that the moon was formed when the Earth was still in a somewhat liquid state, and a giant astral body, like a comet or something, or asteroid, hit it and knocked a whole mess of material out away from the Earth. And then that material formed into the
little
moon,
Earth baby.
which is the moon. When that happened, the moon was like 16,000 miles away from the Earth, which is, if you looked up in the night sky, it would be like all you could see.
Huge.
Be huge.
It's drifting away.
It's
right?
drifting away.
The moon is drifting away.
It's so big.
I think it like a kilometer a year or something, which is not a lot.
No.
But
if you could see that, it would terrify you.
it might even be less than that. But it's 234,000 miles away, I think, right now. And I think before the sun explodes,
Which it will.
the moon is going to be so far away that the effects of the moon's gravity will be negligible on Earth, and the tides will stop.
And then that, tidal almanac companies will be out of business.
If you have property in Miami, sell it.
Dump it.
Dump it. The beach is a joke.
And going back to black holes for just a moment,
Do
Yeah.
it.
tidal forces are what kills you when you go into a black hole. If you, as a person, spaghettification.
Spaghettification. Oh,
Yeah.
I wanted to make that a joke.
What?
What?
What happens is
Spaghettification?
it's
Actual
not.
term.
It's not the mass. It's not the mass or the pole of the black hole that kills you. It's the difference in the pull between your feet and the
And your
rest of your
head.
body when you hit it. So
Does it make you spaghetti?
yeah, the smaller the black hole is, the faster and worse it's going to kill you. Because a big black hole, even though it has more mass and can pull more stuff from farther, doesn't really have any more of a pull than a small black hole, because either way, it's at least strong enough to make sure light can't get away by definition. So a very tiny black hole won't pull stuff from very far away from it. So say one was to show up in this room, but it was the size of a pinhole, or, just for fun to imagine.
Yeah.
It might not kill us, but it would destroy everything like in its immediate vicinity, but it couldn't pull that much, as opposed to like the supermassive black hole, which could reach the entire span of the galaxy, but it's not pulling it instantaneously. It's going to take billions of years.
Which is happening right now.
But when your feet reach the event horizon, which is the point of no return, what's going to happen is you're being pulled.
Great movie.
Event horizon. You're being pulled.
Is Sam Neill in that movie?
Yep.
He's great.
And 2 of the 3 velociraptors from the first Jurassic Park.
in the romantic leads.
Yeah.
So your feet are being pulled into the black hole at such a faster rate than your head is, that your head doesn't notice the difference yet, but your feet
But
are
before you
being
know it,
stretched and you just turn into
you're
spaghetti. But it doesn't just happen vertically. It doesn't just happen up and down. You get pulled atom by atom apart, and you get pushed together shoulder to shoulder. It not only gets pulled all apart, but then it compacts in again tighter than it ever could have been. It's the worst.
Now,
It doesn't just do that to you, it does it to stars.
continuing this, the effects of gravity affect matter the same rate that light is traveling. The effects of gravity essentially make time relative, I guess would be one way to say that. Is that people say time is relative. If you and I were in a spaceship just outside the event horizon, we're floating around in space, we come across a black hole.
Look at that black hole out there. Dan, I'm gonna go check it out. You stay here and man the controls. I got it. I'm gonna get in a spacesuit and step outside. Go for it. Good luck, buddy.
As I start floating towards the black hole to get a closer look, once I cross the event horizon, my fate is sealed. You are outside of the zone of no return, the event horizon, and you're observing me essentially slipping into the black hole. My experience is the spaghettification.
I am being spaghettified.
But that's happening at such a pace, with such a localized sense of time.
So you feel it.
I'm
You
dead.
feel
I'm dead years, like millions of years before I disappear from your view.
So we're talking about Interstellar.
Interstellar is talking about us.
So we have all this math to back up what's happening there, but we don't have a clue what it would be like.
Don't really know.
That's the thing about
That's why I was asking about who can explain what it actually feels like to be in zero gravity.
I suppose that's the same way as like trying to tell somebody what an apple tastes like.
Maybe
It has these qualifying characteristics, but you don't really know. It's like something.
you don't really know unless you actually
Describe
experience it.
Describe red.
You
to someone
don't know
who's
what
blind.
it's like to be
Right.
in space, spinning around in a spaceship, separate from the gravity.
You just have it, separated from Earth's gravitational pull. There's still so much gravity out there. And acceleration in any way mimics the same thing as gravity. So when you're accelerating out in space, even if there's no gravity, being pushed in one direction mimics gravity to whatever extent you're being accelerated.
This ties to like fighter pilots experiencing like 9 Gs in a turn. It's like they're still technically under the same effects of Earth's gravity, but they're accelerating at a rate that is so far beyond. The gravitational constant is changing, in their matter.
I just want to take a moment to shout out to my co-host here because you guys have done an exceptional job today.
Thank you.
You've
Thank you,
really expanded and blown up and imploded my mind a few times this evening.
Gravity is really, really interesting.
It's really cool. Well, this has been great.
This has been a real good time. I'm Martin Wallace.
I have a face for radio.
And I'm Dan Fury.
That guy's not real.
But we should do this for him, though.
We're doing this for Barry. Oh, Barry. Well,
Pass me that blush.
Man, once again, I'm just so glad that Dan exists. so
Me
that
too.
All the stupid shit I say doesn't make it.
Edited.
3 wolves are a pack. 4 wolves are a massacre.